Here's problem 34-7. Determine the amount of energy carried in 1 meter of a 3.5 milliwatt helium neon laser beam if the cross-sectional area of the beam is 5 times 10 to the minus 6 square meters. Alright, so we have a laser beam, and we're just going to consider a length 1 meter of it. So there's our length L. And we have a cross-sectional area. So this is our whole energy inside this beam. And that area is given as 5 times 10 to the minus 6 square meters. Alright? So the volume of this beam is going to be equal to this cross-sectional area times this length, the volume of that cylinder. Alright, we know that the power is 3.5 milliwatts. 3.5 times 10 to the minus 3 joules per second is a watt. And so that's energy per time. So what we want to know is what's the energy inside this cylinder. Total energy will equal the energy density times the volume. The energy density is the energy per volume. And if we multiply by the volume of the cylinder, we would get all the energy inside that cylinder. The energy density U is, well, ICU, so U is equal to the intensity divided by the speed of light. Volume is the cross-sectional area times the length. Now the intensity is the power per area. So we multiply that by the area times the length and divide all this by the speed of light. We'll get the total energy inside that cylinder. Cross-sectional area cancels out, so that was actually extraneous information. And this would be power times length divided by the speed of light. So in this case, that is going to be 3.5 times 10 to the minus 3 joules, which is joules per second, times 1 meter over the speed of light, 3 times 10 to the 8 meters per second. In terms of units, the meters cancel out, and in terms of seconds cancel out, so we're going to end up with joules. This gives us an energy equal to 3.5 times 10 minus 3 times 1 divided by 3 to the 8, 1.17 times 10 to the minus 11. 1.17 times 10 to the minus 11 joules. That is the energy contained in 1 meter of this laser beam. You know, an alternate way to think about this is power is energy per time. So this beam is being put out 3.5 milliwatts or joules per second. If we knew how many seconds it took light to travel 1 meter, then we can think of the energy that would be distributed over that amount of time. In other words, our distance, L, is going to equal the speed of light times time. So the time we're talking about is the distance divided by the speed of light. And we know that energy is equal to power times time. So that would be equal to power times this time, which would be L divided by the speed of light. And hence we're getting the same expression that we just got. Power times length or the speed of light. And when we put in the same values, we will get 1.17 times 10 to the minus 11 joules. Just an alternate way of thinking about the same problem, but we would get the same answer, 1.17 times 10 to the minus 11 joules.